Problem number 4, homework number 1, do two different proofs proving that if two sets are subsets of each other, then these sets are equal. And we need to have these definitions. They're very important. There are two definitions here. One is saying that A is a subset of B if and only if for all elements of X, where X is a member of A, then X is also a member of B. Basically, all this is saying is that in order to claim that A is a subset of B, we need to check every single item inside of A and assert that that item is also in B. And we can see here that this is a subset. And in this case, it's a proper subset. And then also, A is equal to B if and only if. We basically have the same thing. The only difference is that we have this now two-way implication saying that for everything that's in A, that is also in B, and for everything that's in B, that is also in A. And this is a biconditional, and if we have a biconditional, what that means is that P implies Q, and, this is an and symbol, Q implies P. And from this definition of what it means to be a subset, right, we're saying up here that these are both subsets of each other. So what that means is, for all X, where X is a member of A, it is true that X is a member of B. And for all X, where X is a member of B, that X is a member of A. This is just based on our definition. We're proving that two sets are subsets of each other, right? So based on that definition, in order for two sets to be subsets of each other, we have to have this case. In English, all we're saying here is that A is a subset of B, and B is a subset of A. And we can do that because that's basically what the premise of the question is. We're saying right here that we have two sets that are subsets of each other. So all we're doing is writing this in a more formal way where we have our definition. This is what it means to be a subset. For all elements X, X is a member of A. We're just rewriting it in terms of this formal definition that we have up here. And then we could just combine these statements. X is an element of A. Right, we haven't done anything. All we're doing is we're just kind of pulling out this for all X out. It doesn't change the truth or the implication of this sentence here. But what we can see here is that we have this P implies Q, and we have Q implies P. And because we have this format, we can just say that it fits our definition here. P implies Q and Q implies P basically means that we have a biconditional. Therefore, for all elements X, if X is a member of A, it is true that X is also a member of B. And we're done. Now, alternatively, we can do a proof by contradiction. Suppose that A is not equal to B. This means that there exists some element X such that this biconditional statement, which is our definition of equality, is false. As such, one of two things must be true. There exists some X that is an element of A such that X is not an element of B, or there exists some X that is an element of B that is not in A. And if that's the case, by definition, it cannot be a subset. Either one of these has to not be a subset, or both of them are not a subset. And this ultimately contradicts the definition where we say that A is a subset of B, B is a subset of A. Or if you wanted to write it out like this, I don't have much more room to work with, you can write it out like that. Therefore, it has to be the case that if two sets are subsets of each other, then those sets have to be equal.